Hey everybody, how we doing today? I hope you're doing as awesome as I am, because I am super psyched, because today we're going to talk about two things. First thing we're talking about is what makes a strong acid and strong base versus what makes a weak acid and a weak base. So what is it that makes an acid or base strong versus weak? Because if you remember before, it had nothing to do with how concentrated it is. There's something else. There's a different way that we label an acid or a base as strong versus weak. It doesn't matter how concentrated it is. It has to do with how the thing performs when you put it in water. And the other thing we're going to talk about is how to name an acid and a base. Because if we're going to be talking about acids and bases, we should be able to talk about them. I mean, that just kind of makes sense, doesn't it? I think it makes sense. Sweet. If it doesn't make sense to you, just replay it. It'll sink in eventually. All right, so here we go. What is it that makes an acid or a base strong versus weak? Let's start with the strong ones, because it's right there. So let's just do it. So strong acids and bases, what makes them strong is the fact that they dissociate completely in water. Now that's a really fancy word, and we should really dig in to make sure we know exactly what that means, because it seems like a pretty sciencey word. And instead of giving a big definition, I want you to look right there at that arrow. Okay? You see this arrow inside this here chemical reaction? What does that mean? Do you guys remember what that means? Yes, it means it goes that way, and that's it. It just goes. Does it go back this way? Nope. Once it goes, it's done. It's not going back. This is non-reversible. And that is what dissociate means. It means it breaks apart and it stays apart. It's like a non-reversible kind of breakup, right? So when we take HCl and we dissolve it in water, this stuff dissociates into the hydronium ion and the chloride ion, and they stay ions. That's it. They break up. Done. Over. That is what it means to dissociate, to permanently break apart. Now, same thing with strong bases, only when it's a base, all right, we've got our hydroxide ion there. And if you'll notice, one-way arrow, this is not a reversible reaction. So when this dissolves into water, it makes a hydroxide ion and a sodium ion, and they stay ions. They break apart, they stay apart. That is what dissociate means. And that's what we mean by strong acids and bases. So when we put it into water, it breaks apart and stays that way. So all of the hydronium ions are available to be acids, and all the hydroxides are available to be acids. Which, believe it or not, is not always the case. Because when you have a weak acid or a weak base, they partially dissociate. They partially dissociate. This is really important. And to understand that, I want you to look at this symbol right there. Right? So what that means is that the forward reaction happens, then the reverse reaction happens. Then it breaks apart again, but it gets gets itself put back together. It's a reversible reaction. So what happens is, let me get something here, that this wonderful dihydrogen sulfide, when it's dissolved in water, it will create two hydrogen ions. However, it will go backwards, and it'll go back to the reactant. And when it goes backwards and it's in the form of H2S, what that means is that these ions are no longer floating around. They're no longer available to be acids. They're back to H2S. Does that make sense? So if it's a reversible reaction, it means that once they break apart, they can often snap back together. And when they do that, when they snap back together, they're no longer ions. So they can't be acids or bases. It's like they're being acidic or they're being basic part-time. Right? Sometimes they're there, sometimes they're over there, sometimes there, sometimes there. Same with this guy right here. You notice this wonderful symbol right here means that this hydroxide is going to be there, but everything's going to go back, right? So this hydroxide is going to disappear back. Where'd my pen go? It's going to disappear back over. Wow, that's the worst arrow I've ever had. That here, there. That's terrible. So it's a reversible reaction. Weak acids and bases are reversible reactions. They're in a state of equilibrium, which means that the product is not always there. It is not always available. You got it? So it can't always be around to be acidic and be basic and stuff like that. So it is really, really important for us to have locked in our brain the idea that concentration alone does not determine the strength of an acid or a base. It is the ability to dissociate. It is the ability to dissociate in solution that really determines whether we call it a strong or a weak acid or base. Now, concentration is a whole different ball of wax. You can take vinegar. Vinegar is a very weak acid. It's only broken apart, I think, like 20 or 30% of the time. The rest, it's like the hydrogen ions are still bonded into the molecule. But if you made vinegar concentrated enough, like with the stuff that we get at the store is usually like 5%. But if you made it concentrated enough, you wouldn't be putting it on your salads because it would wreck shop. But even if it was very, very, very concentrated, it is still categorized as a weak acid. Okay? Okay. Because honestly, if you took like hydrochloric acid at the same concentration that we eat vinegar on our salads and stuff, if you poured hydrochloric acid on your salad at that concentration, the concentration of vinegar, I don't think you'd have a salad. It would be like a bowl of ugh. So there is a word here. So we have dissociate. I just used that, and I didn't explain what it is. And to dissociate is that's when ionic compounds totally break apart and form ions. That's like the definition. It's when they completely break apart. And I don't have it in here, but it should be and they stay apart. So dissociation is when ionic compounds totally break apart in a liquid to form ions and stay apart. You got it? That's how we get the strong and the weak. Now this other one, there's going to be another one. I'm going to jump down here. It's this one. It's ionization. That's the opposite. But we'll get there in 1 second. So, oh yeah, also strong electrolytes. Anything that dissociates, we're going to call it strong. So let's see if we put this into liquid. Do you see this arrow? If we put this into water, what are my ions going to be? Well, it's going to be potassium and it's going to be bromine. Right? The reason why I'm doing this is I want you guys to start noticing and looking at and honing in on what are the ions that are going to be formed. So if it's making potassium ion and bromine ion, is this thing going to be an acid or a base or a salt? Yep, it's a salt because it's ionic and it's not an acid or a base. Now this one, magnesium hydroxide, what are my ions? Magnesium, that's a 2+, and OH. Base. Totally. You see how that works? Now we have HNO3. Now I'm noticing that there are, what I've got here are 1, 2, 3 capital letters. Probably a polyatomic ion, right? Because remember, we're not going too crazy here with stuff just yet. So I'm gonna break out this to help. Table E, if I remember correctly. Oh my gosh, I totally do. Oh, yep, NO3 is a polyatomic ion. So what I'm going to get here is I'll get the H+ ion, and I'll get the NO3 minus ion. All right, this, oh, acid. I almost thought that was going to be salt. Okay, now this one, 1, 2, 3 polyatomic ions. Give me a minute, let me check. Yep, oh my gosh, there's a polyatomic ion there. Weird. So we will get, in this one, we'll get 3 hydrogen ions, and we will get a PO4, polyatomic ion. Oh, yep, definitely an acid. Lovely. Let's move on to this one, the ionization. Now, we were talking about dissociation. This is like the other part. This is ionization. Now, this is where things break apart, but then they get right back together again. And the thing that's pretty clutch here is this is from covalently bonded molecules. Pretty much anytime you see carbon-based, it's gonna be like that. Now this is when they break apart. It is a temporary break apart. Temporary breaking apart. Okay? Like I said, it's like 20 to 30% of the time where they're actually apart, and then they snap back together. And then you don't have the ions floating around, so you don't have your acid or your base. And again, the thing to watch out for is this guy right here. This is the symbol you need to watch for. Okay? And I chose this guy. This is acetic acid. right? And I chose this one on purpose because I want to talk about what happens. So this is an organic acid. And so what we do to show where the acid part is, the part of the carbon molecule that's actually acidic, is this. Anytime you see this pattern, COOH, you know it's going to be an acid because it is this hydrogen right here that breaks off and makes the hydrogen and like dissolves into water and makes the hydrogen ion. So what we get after that breaks off is CH3 COO with a -1 and a hydrogen ion. You guys get what I'm saying? So I just want you to recognize that anytime you see this, that means it's going to be an acid, okay? And that also means that it's going to be a weak acid because it's carbon-based. And it's this guy right here. This is the guy that like breaks off, okay? Lovely. I think that, oh my gosh, it does. It covers everything about like strong and weak. I don't know if we could go anymore. I mean, we could keep talking over and over and over, but let's not. Instead, let's learn about naming these bad boys. Because now that we know how to name them, we're gonna like move forward and we're gonna start talking about how they interact and how they do chemical reactions and how we use them in titrations and like all kinds of crazy stuff. So if we're gonna talk about them, we should really know their name. So here's how we do. So binary acids, these ones are easy. There's binary means 2, okay? So binary means 2, and for us it'll be 2 ions. That's all it is. So these are the very simple ones, and it will be hydrogen, and it will be 1 element, right? So it'll always be like H plus a negative ion, and here's how we name it. For the hydrogen, we say hydro. Now remember, this is only for binary. This is only for binary, okay? So the hydrogen turns into hydro, and the negative ion, we end in ic. And that's it. So for example, this bad boy, right? This is binary, 1, 2 ions. Okay. Okay. Or I'm in elements. Sorry. So the H turns into hydro. The chlorine turns into chloric, and then you say acid. Yeah. I'm going to change that ions. I'm going to change that to elements. I think I may have misspoke a little bit, enough to make things kind of confusing. So I want to change the binary definition to 2 elements, not just 2 ions. That might be a little confusing. It's 2 elements will be I think that's going to be a better definition for us. There, like these guys. And you can see only 2 elements, H and F. So if you see something this simple, right, there are only 2 capital letters. This first guy, the hydrogen, turns into hydro. Now remember, we only do that when there's only 2 elements. And then the F is for fluoride, so that turns into fluoric acid. Hydrofluoric acid. All right, see? 1, 2 elements. 1, 2 elements. Awesome. So this will be hydro, bromine, bromic. Hydrobromic acid. Now this one is going to be named the exact same way. 2 capital letters, so there's only 2 elements. So I'm going to say hydro. And then iodine, iodine got to end it with ic, so it'll be iodic. So hydroiodic acid. That's super simple, right? Hydrochloric acid, hydrofluoric, hydrobromic, hydroiodic. We can do these. These ones are easy. We can also do these ones, the ternary. Now this is why I wanted to say elements instead of ions a little bit earlier. That was a little bit of a mistake. So ternary, this means 3, right? That ternary means 3 elements. And this is when we have hydrogen and a polyatomic ion. Okay? Now this one, polyatomic ion, makes it a little bit weird. The hydrogen dropped. We don't say a thing. So if there's a polyatomic ion, we don't say hydro whatever something, or you just drop it out. Because if there's a polyatomic ion, that's enough. And here's how it works. What you do is you take the name of your polyatomic ion, and if it ends in 8, it turns to ik. If it's ite, it turns to us. Okay? So it goes 8 to ik, it goes ite to us. Okay? I want everybody to say that together. It goes 8 to ik, and then ite to us. Can we do that just one more time? It goes 8 to ik, and then ite to us. 8 to ik, and then ite to us. It goes 8 to ik, and then ite to us. You feel that? You feeling it? I know you can feel something happening there. There's some kind of magic going on. I'll tell you that. You can't feel that. You're not alive. All right, so here's how it works. I see 1, 2, 3 capital letters. I must have a polyatomic ion. So if I go to my table E, I look up NO2, and it is called a nitrite. Okay? This is called a nitrite polyatomic ion. So 8 to ik, ite to us. So instead of saying nitrite, we say nitrous, and then you say acid. That's it. Nitrous acid. 8 to ik, ite to us. All done. Now this one, oh yeah, NO3. If I look up on table E, it is a nitrate, and it goes 8 to ik. So it turns into nitric acid. And that's all you do. If you notice, when you have a ternary acid, there is no hydro. It's only for like the doubles. Something like this with a polyatomic ion, no hydros. Got it? Great. Now, let's try naming some of these bad boys. Okay, so SO3. One, two, yeah, look, these are all polyatomic ions. So this will be easy. I'm going to start them all with hydro, right? Please don't do that. So, SO3. I'm going to come over here and I'm going to look up SO3. Oh, there it is. It's sulfite. S-U-L-F. 8 to ik. Ite to us. That's all you got to do. Now this next one, CrO7, I think the hardest part of these is actually like finding, like making sure that you're finding and looking up the correct polyatomic ion. So Cr2O7 is dichromate. So that's di. 8 to ik, ite to us. Chrome 8 to ik. Dichromic acid. Are you picking up how this goes? SO4 is sulfate. See right here, SO4 is sulfate. Easy peasy lemon squeezy. All right, next, HClO4. ClO4. Where, oh, there it is. Perchlorate. All right, you turn 8 to ik, and they call it acid. That was easy. Guys, this is so easy. ClO, hypochlorite. Ooh, I'm going to have to spell that one. Okay, it goes 8 to ik, ite. Lovely. CrO4. Oh, that's right there. Chromate. 8 to ik. See? Right here we have the chromate. 8 to ik. Chrome 8. Chrome ik. Easy peasy, guys. Like, no worries at all. That's so easy. As long as you have that reference table. Man, if you don't have that reference table, it's going to get really hard. Now let's move on to the bases. Boy, this is really hard. I'm kidding. This is the easiest thing ever. So for binary bases, it's going to be like some kind of positive ion. Typically, it's going to be a metal, and then you'll have your hydroxide. So this is what we do. For that metal, the name doesn't change. You just say it, like whatever it happens to be, and then you say hydroxide. That's all. That's all there is to it. So for example, this one, this is sodium, right? I just say the name, and then I say hydroxide. Super crazy, huh? That's all there is to it, guys. That's all there is to it for all these. This one, magnesium. Magnesium hydroxide. Super simple. This one right here, this is where we have potassium bonded to a hydroxide ion. Jeez, I don't know what that might be called. Let me think for a minute. Yeah, potassium hydroxide. That's it. And then this weird compound here, where lithium is bonded to hydroxide. What could this possibly be? I have to think on that one for a minute. Yeah, lithium hydroxide. Yeah, so not crazy hard to name the bases. So we're done. Lovely. We will practice naming these, and I hope that you guys have a lovely rest of your day. I plan on enjoying the rest of my day, and I will see you guys very soon.